our first presentation for today is automated testing using reinforcement learning. In this talk, Brad will explain the underlying technology behind Kwola, a next-generation tool for finding bugs in web applications. He will explain the basics of how Kwola works, what makes it learn, how the neural network is designed, and will conclude with a short demo. Brad is an accomplished engineer working in the AI industry since its popularization in 2014. He was one of the first employees at Sensibill, where he built deep learning technology to understand receipts. In 2016, he founded Electric Brain to build custom AI technology, which was later acquired in 2019. He's now developing Kwola, which uses reinforcement learning to help automatically find bugs in web applications. Brad visited AI Geeks, the previous name of Soft Geeks, many times in the past, and we are happy to welcome him again today. Brad, feel free to take over the presentation.
Thank you everyone for coming, and I'm super excited to talk about this technology. I love talking about it, I'd just like to start by saying, like, the reason I came up with this Kwola, frankly, was, I've been in the startup scene a long time, pretty much my whole career. It's all startups and young companies and whatnot, and I'm always constantly embarrassed when we're up in front of like an important customer or an important investor or an important client, and I'm demoing some code and the code breaks right in front of me and right in front of the investor. That's frustrating, and not to mention frustrating, it kind of reduces your reputation. Even if you try to set expectations, you're like, oh, we're showing something new, it's like, things may go wrong, you're seeing the cutting edge, nevertheless, those moments are embarrassing. And, I knew this was a problem, and I wanted to come up with a solution, but, it was important to me to come to solve this problem. Also partially just because I'm known as a person who creates a lot of bugs. So, if I could use my skills of programming to solve bugs, that would help a lot, because, I don't want to have the finger pointed at me all the time, every time, something crashes or breaks. And it was often me, frankly, let's be honest here. Kwola, I knew about the problem for years, and the solution literally came to me like a lightning bolt. I remember the day, and I don't know how it happened, but at some point in time during the day, it was just like the idea like came down from the sky, slammed into my brain, and I jumped out of my chair, and I'm like, oh my God, I can solve this with reinforcement learning. Like that's how we can automate the browser. Like that's what's going to drive this AI technology. It's like, I'm certainly not the only one who's thinking about how do we apply AI in web browsers. Yeah, the idea for Kwola, it all just kind of came together, and that's what I'm about to show you. So let's jump right in here. Share my screen, desktop, share, beauty. All right. Okay. Let's go to this presentation and full screen. There we go. Oh, come on. It doesn't want to reliably. Doesn't like my F1. Okay. Well, we'll just do this. It's full screen enough. It's like 99%. All right. So we're here to talk about how do we automate testing using artificial intelligence and reinforcement learning. I'll just take a moment to talk about our goal. So, what we're trying to accomplish with Kwola is not just some sort of visual comparison tool or some new way of writing tests. Like I've seen some of what you might call our competitors. They're trying to make it so that you could write a test in English, and type it out. And that's kind of cool. I don't get me wrong. I love that. The size of the data set they need to make that really work is enormous. But um, what we're trying to accomplish here is how do we test software with literally nothing, with no time or effort, no humans, no writing tests, no engineering effort, no ongoing maintenance. Is there a way that we can test software based entirely on its own merits, on the software itself? And you know, existing solutions are enormously costly. They you know, if a team is really good at testing software, you know, they are spending 50% of their engineering time writing tests. Like that might be called the gold standard. Um, if you map that out to, you know, dollars in a year, that easily adds up to $1 trillion worldwide is spent on writing tests. Just in terms of the salary that is paid out to engineers, it's very large. So existing solutions, you know, we need something better, especially for startups where we're always starved for the amount of time required to test software. So the fundamental problem is how do we learn how to use a website with AI? And it's not even specifically a question of how do we learn how to use a website. It's like, how do we get an AI to learn how to use software itself? The way I'm seeing the problem, it's not so much about teaching an AI to find the bugs. Like, how do we make an AI that can find bugs? I watch a lot of these speed running videos because, you know, video games nowadays, there's nothing else to do. And it's amazing how people can find glitches in video games. Like, video games by far and away are the buggiest type of software. You know, we're not teaching an AI the way that these people do. How they find a glitch is often like running into a wall 1,000 times and eventually they go through it. You know, we're not trying to do that with software. The way I visualize this problem, it's not so much about teaching the AI to find the bug. It's just, how do we teach the AI to use the program? How can we have it go through and trigger all of the different features, all of the different pieces of functionality? And as long as we can get it to kind of thoroughly test the program the way a human manual tester would, then we already have something useful. And so the idea, we're going to discuss this further, so don't get too detailed, too hung up on the graph, but I'll show it again. But the solution for me was, as it often is in things that I work on, a neural network. And if we got the design of the neural network right, the software could, the network could learn to use the software. You know, we've seen neural networks learn to play Atari games, Super Nintendo games in some cases. Now they're talking about Dota. They're talking about, I think it's like StarCraft. You know, we've beaten Go. Those are fun, but can we take the same technology, the same learning mechanism, and apply it on just like a regular old application? And so the design of this neural network, not surprisingly, you know, we have a website. We start with, I can't click, I guess. Yeah. We start with the website, and part of it is processing the screenshot, as you might be familiar with, like any sort of like ImageNet or image processing network. We send the screenshot through. But the other part of the design of what we're doing is actually, how do we measure the code that was executed? And so I'm going to talk about this further, actually. Let me just go on this slide. I'll come back to this image later. So the TraceNet is based on the same stuff that DeepMind is doing. You know, it uses their it's like 5 years old, but A3C was like very innovative when it came out. I guess 4 years old. It's the same type of neural network that they're showing that can beat Atari games and can beat Dota and all of that. And we try to take advantage a lot of the innovations that people are kind of showing works in the papers. The key basis, if you know nothing about reinforcement learning of A3C, is basically that the neural network is optimizing to maximize a reward. And specifically in A3C, we kind of set it up in a way where you have a bunch of AIs out there interacting with the target piece of software and measuring how much reward they're actually getting. And completely separately, in parallel, you kind of have this brain that is like learning from that data that's being gathered. And like the two kind of processes go in lockstep with each other. Frankly, it's not that innovative in terms of reinforcement learning. It's obvious now. Imagine like in 2015, this was mind blowing. But yeah, now to me, it's almost like, yeah, it is what it is. Anyhow, so the way that Kwola works is it boots up a web browser. It loads up the target URL of the application, and then it starts taking a series of actions on that web application. Much like those video game AIs, they'll load up some game and they're pressing the A button or the B button, the up arrow, down arrow, whatever it is. For us, the actions involve, what you might do on a website, which would be like a left click, a right click, scroll up, scroll down, drag and drop. We don't actually have drag and drop implemented. We're getting to it. There's not that many websites that use drag and drop anyhow. But and then typing. Typing is probably the hardest one. That's the one that kind of like a click is just one action, but a keyboard has like 70 or 80 keys. So teaching the AI how to type is the sort of more challenging piece of this. A little bit of this is outdated, so we actually don't do 1,000 loops anymore. Now it's just indefinite. That's the basic idea. It's like booting up a set of web browsers and kind of iteratively performing a series of actions on it. Now, we need to measure what is actually happening in response to the actions that we perform. So it's like, I click on this button and I see that these lines of code over here get executed. Whereas if I click on this button over here, I can kind of see, oh, it was these lines over here. The way that we do this in Kwola is that we actually we sit as a man in the middle. It uses a proxy, basically, a HTTP proxy, and we can rewrite all of the JavaScript code that goes through Kwola. So when Kwola boots up the Chrome browser and it points it at your URL, we can just sit in the middle and we can detect, oh, that's JavaScript code. Oh, that's HTML. Oh, that's CSS. That's an image. And then we can break all of those things apart, take that JavaScript code, and essentially rewrite it in much the same way you would a profiler. A lot of people, if you've ever used profiling, it's to help you identify the slow parts of your code. Kwola does effectively the same thing. And here you can actually see it. So this is the rewritten code. I guess I don't need to zoom in, but you can see there's some underlying Angular code here. I guess you don't even see the Angular code in this screenshot. But you can see Kwola injects a big array with all of the different branches of the code, and it increments different portions of that array for each of the branches. So we don't need to count like every single line. You could have 50,000 lines of code, but if several lines are consecutive, like they're all getting executed. So what we actually only count are like the functions and the branches, everything you might associate with like a curly brace. And that because all these lines are correlated anyhow if they're consecutive. So here, yeah, that's the rewritten code. Just as a side note, this there's the AI is not affected by changes in the code as long as the changes in the code are not too serious. And it's pretty simple. I mean, we use basically the same diff mechanism that your repository control uses. And we can just look at the old version of the code, the new version of the code, see the changes, and we can line up the mapping of the old lines of code to the new lines of code, based on that diff. And this works even in minified code or complicated JavaScript situations, as long as you haven't, it's not like a total rewrite. Like Kwola is kind of more designed for continuous integration teams where it's like you're writing code and you're pushing code and releasing it every Friday or every 2 weeks or every 3 weeks. It wouldn't be so good if it's like, oh, okay, we want to test it this year and then wait 9 months and test it next year. It's kind of, then the AI, it's not going to be able to line up every line of code because if you've rewritten those sections, then we have to kind of map those to new symbols within the neural network. We're kind of more designed for where you're changing, some section each week and continuously integrating, and Kwola can kind of adapt to those changes in the code over time. Another question you might ask, like, so going back to our design here, let me scroll back. One thing you might notice if you're an astute sort of neural network observer is that this is only a feed-forward network. There's no loops. It's 100% one action at a time. And you might think, like, how could Kwola possibly work if it has no memory or no ability to even know what it did, the last action, what button did it click on, or, what menu or screen did it go to? In practice, this is not actually necessary. So the way that Kwola works with a memory is more that we measure which lines of code it triggered based on all of its actions, and we feed that as an input to the network. So if it hit this button and these lines of code got executed, and I hit this button and these lines of code got executed, and there's some sequence there, we can feed it an input with all of the different lines of code that it executed, and then it can just automatically kind of infer, oh, what is the next thing that I need to do? So it doesn't really need a memory or an LSTM or even an attention layer, although I have been experimenting with attention in other ways. It can actually work as a 100% feed-forward network, and it can still resolve the list of actions. So coming back, here's another kind of interesting thing about working on websites. When you compare a website to like those Atari games, the Atari and like the Nintendo, they have like less than a dozen buttons. Where when you're interacting with a website, it's not just that you can click on all these different spots on the screen, and they may all do different things. So if we look at the number of possible actions that you can take on a website, it's kind of enormous. Like we have left click, we have right click, we have typing something in, and we have it at every pixel on the screen. It can be tens of thousands of potential actions. This is really not good for reinforcement learning. Reinforcement learning, it's all just statistics at the end of the day. And for any statistical analysis to be worthwhile, you need kind of like 1,000 examples. Like that's a rule of thumb, but you need 1,000 samples. And if you have 10,000 pixels on the screen, to get 1,000 samples of clicking on all 10,000 pixels on the screen, what's that? That's like 10 million data points. It's a completely ridiculous and would completely make this approach invalid. So that what we have to actually do is not click on everything, or every pixel on the screen and try to exhaustively reduce all possible behaviors of every pixel. HTML makes this a little bit easier. It's not quite as easy on mobile apps, but with HTML, we can just go in and we can be like, oh, that's a button tag, that's a div tag, that's a link tag, that's an a tag, whatever it may be, and we know how to interact with that now. We know that an input element, you type into that unless it's a select element. We know, or radio button. Don't not get started on that. Also, if it's a button that's clickable. But we also can use a few other heuristics. So if it's not just that the tags are clickable, we also intersect with the event handlers that are assigned in the JavaScript. And if you assign any click event handler to any div tag on the page, we'll just detect that. We know, oh, that element is clickable. It's responding to clicks. And so now Kwola is no longer clicking. We no longer need to teach the reinforcement learning algorithm about every single pixel on the page. Now we've reduced it down to a manageable size, because the more human interpretation of a web page, it's like, okay, I've got 10 links on the left. I've got 3 buttons. I've got 10 input boxes. I've got a save button down here. I've got a cancel button over there. Well, that's what I have to interact with. So we're trying to reduce the way that Kwola works to be in line with kind of our human expectations. And this is something you're going to see all over artificial intelligence, is constraining the algorithm is really important. You have to constrain it to keep the amount of data that you need to gather within reasonable terms. Reinforcement learning can learn across a very wide variety of situations. We didn't need to do this reducing thing. We really could gather the data on every pixel, on everywhere on the screen, clicking, typing, right clicking, whatever. But if we reduce that a lot, we don't need to. Another important thing to note is with reinforcement learning, there's always a question of what do you do before you know anything, before you've actually learned anything, or alternatively, it's how do you discover better behaviors or better things to do? And with Kwola, like any other form of reinforcement learning, this involves randomness. So Kwola is always operating on some mix of the predictions of the neural network and completely random choices. And in fact, the better that we can design those random choices so that they're more likely to be leading to the reward, I'll talk about the reward later, the better that the algorithm learns. The way that Kwola works is we have the pure random action. This is similar to a fuzzer. It's pick an HTML element at random that we know is interactable, pick an action associated with it, and perform that action. And there's some weights in there, right? So Kwola prefers to interact with things on the same page rather than switching to another page, and a few other kind of heuristics that are in there. But we also have the weighted random. The weighted random takes the values predicted by the neural network and just uses those to make a kind of probabilistic choice of which button to click on or which link to click on. And then we have, of course, the prediction of the neural network, which is, that's basically, it's what pixel do I click on that gives me the highest reward? Or alternatively, what HTML element or what button do I click on that gives me the most reward? And so here you can actually see an image of maybe a little bit of a visualization of what this looks like. So on this image, of course, on the left here, we have the software, the application itself. And on the right, what we have are the reward predictions. Actually, these are different. These are not even all I guess they're all reward predictions in some way, but they're all the predictions of the neural network. And the lighter it is, the higher reward that Kwola predicts for that spot. And the lower it is, the lower reward that it predicts for that spot. And we, what you're seeing, there's multiple images here that include predicting like the reward on the very next click, but also predicting like if I go to this screen, what is my reward going to be over the next like 10 or 20 actions? There's like an exponential discounting there. Then that we also predict how much reward are we expected to get versus the average reward. And this is called the advantage value. It's like just how much better am I doing than average. It's kind of like a slight modification of the previous two. And then there's the final one is called the actor. That's basically just, it's not so much what is the reward, it's like what should I do now? And it's a slightly different prediction for that neural network to make. Is versus I'm not predicting the reward. I'm just like, okay, I have 5 buttons I can click on. Which one should I click on? And that we train the actor just based on the advantage values, and the advantage values are also in turn based on the present and discounted future rewards. And you can see this all playing out kind of on this screen here, where we see different values. So what is the reward? When DeepMind is playing video games, the reward is beating the video game. Or sometimes they even use a simpler reward, which is just increasing the score. It's like, if I increase the score, I got a reward. If I didn't increase the score, no reward. So, logical question being like, what is Kwola's rewards? When they're doing that protein thing that now that everybody's, DeepMind, they solve protein folding. In that case, the reward that they're optimizing for is like the energy potential between the atoms. It's pretty cool stuff. So you will ask what is Kwola's reward, and Kwola's reward is triggering code. So going back to the point earlier in the sequence where I talked about we measure what lines of code get executed in response to the actions we perform. If I click this button, these lines of code get executed. If I hit this checkbox and click the button, it's a different, it's mostly the same lines of code, but yeah, a couple of them are different, because we did, went on some other if branch. All Kwola wants to do is trigger all lines of code exactly once. It wants to go to all the different screens that it possibly can and trigger every single one at least once. So this way, it's not getting rewarded for all of the lines of code it's triggered because, it's presumably continuously triggering lines of code. If it's clicked a button and that button works, we don't need it to get rewarded again. Once it clicks that button, it's gotten the reward. We want it to move on to something else. Try the other buttons, test the other pieces of functionality. And this reward is really useful because it aligns generally with the things that we care about in testing world, which is just triggering all of the different behaviors and functionality of the software and making sure they all still work. It's coverage. Ultimately, what we're optimizing for is to maximize the coverage. Kwola wants to trigger all of the lines of code as it possibly can in the shortest amount of time. And if you do that, I'll get to auxiliary next. If you do that, Kwola then, it is effectively learned how to use the software. And not even just how to use the software. This has nice effects, for example, where Kwola will try to trigger error cases as well as triggering the reward case. For example, if you have front-end validation that checks if Kwola has typed in a valid email address, it gets a reward once for typing in an invalid email and making sure that code still works. And it gets a reward a second time when it types in a valid email address. So it wants to do both of those things because, those are different code paths. Another kind of just interesting thing about AI, of course, is that um, we want to give it as much to learn from as it possibly can, and also the reward of triggering code, it's not 100% perfect, because it doesn't work for single page, or sorry, not, it works perfectly for single page. It doesn't work for server side rendering apps, or for certain types of applications where the new behavior is triggered on the back end. So we also analyze other things that Kwola does, like did it trigger an API call? Did it trigger the screenshot to change? How many pixels did it change? Did it change to a new page, or did it stay on the same page? And these additional rewards can help make Kwola's pattern a little more incremental. They're not as large as the main reward. The main reward is still triggering new lines of code, but these ones do as well. This is actually just like the internal data object for a trace, which is effectively the result of us clicking on a button or something else, and like what actually happened. So it's like, did we trigger an error? Did we trigger new code to execute? Did we have new network traffic? Did the screenshot change? Like, you can kind of see all of those features highlighted in this screenshot. And, Kwola is code like anything else. So another thing, although Kwola clicks, like I said before, you can't really train Kwola 1 pixel at a time because it's a little bit ridiculous. What we actually try to do is we train it for roughly all of the pixels in the HTML element. Now we can't do this exactly, because some HTML, you may have overlapping HTML elements, like you may have like multiple things that are responding to the click handler, or you might have an HTML element like a canvas or an editor type thing, where different segments of it cause different behaviors. But for the most part, what we try to do is we try to gather all of the pixels that we think are associated with a particular click, and we use the flood fill algorithm. We actually also now it's changed a little bit, but we now we do kind of like a segmented expansion. So you can see here in this this image here, it is not assigning the reward for the area where the text is. But now it's like Kwola will kind of like, it'll take this like flood fill and then also expand it by several pixels, so that it generally gets all of the pixels that are associated with a particular UI element. Another cool AI thing to talk about is that the reward signal is a very messy, kind of noisy signal, up and down a lot and all over the place. If I clicked on a button, did that lead to a new line of code because I clicked on that button, or was it the checkbox that I clicked right before that button that led to these new lines of code? It's not always clear. And so one of the ways that we help the neural network to learn is we give it more information to learn from. So instead of it just learning purely the reward signal, we also just have it directly predict several things about what's going to happen if it clicks on a particular spot on the screen. So for each pixel on the screen, in effect, what we do is we predict, what lines of code are going to get triggered if I click on these pixels. And by doing this, it makes it much easier for Kwola to learn the reward signal that we actually care about, because you're just giving it more to learn from and more to clarify precisely why it's getting a reward in one situation, it's not getting a reward in the other. Because like what we need to do is we need to have the Kwola network kind of reduce causation. What caused new lines of code to get executed? So coming back to this neural network diagram, now we can talk about it a little bit more. You can see on the left here, we start with the website. All of the lines of code go down here. We count the lines of code. We map them to embeddings the same way a neural network might map, say, words of English to embeddings. We map lines of code to embeddings. We feed them through a couple of layers, and then we map them into a way that they can be combined with the image data. And through the top here, we take the screenshot, we send it through a bunch of layers, and we combine it with the data on which lines of code got executed. So now the neural network can both see what you can see, and it can also see what did I just do. Oh, I just clicked on those buttons and triggered those lines of code. I don't need to do that again. Now I need to do something new. And so this middle vector then goes through, it kind of splits branches off, and then we predict the various probabilities. For example, we predict, are we going to get a reward on the very next action? That's what I call the present reward. Are we going to get a reward in the future? We're expected to get some predicted future reward. If we take this action, that's a discounted future reward. The state value, it's like, what is the average reward that we're expected to get if we take this action? And the advantage is like, how much better is taking this action better than the average? It's like better than the state value, technically. So these two parts of the neural network are compared. And then finally, the action probabilities. That's like what I was saying before. We're not asking the network to predict the rewards anymore. Now we're just saying, tell me what to do. It's like, here's the screenshot. Here's the lines of code I triggered before. Tell me precisely what is the very next thing that I should do that will trigger lines of code that I care about. And so all of the effect of this is that Kwola is able to learn how to use software. It is able to worm its way through from random clicking and typing and just kind of like chaos to kind of like a smooth path through the whole application. And I'll show you a little bit what that looks like. So this network, it wasn't even trained a long time because I spend a lot of time optimizing for early training, like a few thousand browser sessions, because that's just how the Kwola product works. But you can see right at the beginning of the video here, everything's lighting up yellow. It's like it predicts to get a high amount of reward for all of these different screens, all of these different links. If I go there, I'm going to get reward. If I go there, I'm going to get reward. And you can see that in all of these images here, except for the scroll up and scroll down, which my mouse is over right now at the kind of second, or I guess third from the left at the top here. That one is all blue because what it's interpreting in this case is if I scroll, nothing will happen. Like there's no new code gets triggered by scrolling. All of the new code gets triggered by clicking and typing stuff in. So you can see on the click ones, it predicts it brightly. But if we go forward in the video just a little bit, and you can also see on the bottom here, this is the discounted present reward. I call it the net present reward because I did business and I see the equations as being a lot similar to net present value equations in finance. But anyhow, you can actually see it aggregates all of the actions that are going to give a reward near the beginning of the sequence. And you can kind of see that underneath the screen here. But like, let's go ahead to like several actions in. So you can see now on the top here, where my mouse is, I wonder if I need to, can I zoom in? I'll look at it later. That it's no longer showing bright yellow for all of these menus on the left. Whereas before, when we started the sequence, it's bright yellow, it's predicting a high reward Once it's actually visited those menus, it's no longer predicting a high reward for those menus. So Kwola learns to just kind of go through the application and trigger all of the different features and functionality in that software. Now, jumping ahead, how do we find the bugs? Okay, yeah, so this is, I could quickly summarize on this slide. The Kwola is able to learn how to use the software. It goes through, all it cares about is triggering as many lines of code as possible, as well as new screenshots and a few other kind of auxiliary rewards. But the main one is triggering the lines of code. And it actually can learn a lot faster. Like, you know, if you read the research from DeepMind and they're like, oh, we beat Dota, it's like they threw like tens of thousands of servers at the problem. That would not make a very good product. If I went to a customer and said, oh, here's my testing solution, it only costs $100,000 to set up and, you know, $500,000 every time you run it, people would not be so impressed. Kwola, because we don't need any memory, it's fully feed forward. It can learn a lot faster than that. In fact, it can learn in just a couple of days how to use the program on my rig here. And it starts vastly improving over random chance, which is what, you know, previous tools used to do almost very quickly. So, okay, now jumping ahead, finding the bugs. So now you have Kwola, which is able to use the program to trigger all of the different features and functionality in kind of an efficient manner. Now, how do you actually find the bugs? The first way that we find the bugs is just that we kind of bump into them. There's no real magic here. It's just a matter of detecting them within the browser. So if Kwola triggers any like crashes or exceptions, any obvious bugs like that, we can catch them. If there's like a network error, like a 500 error on the back end, you cause the server to crash, we can catch that. And we can also catch all of the instances where something wrong is showing up in the user interface, like you render a null or a NAND. Doesn't happen that often, but sometimes I go on an interface and I click around a bunch and I'm like, oh, null, oh, that shouldn't show up. Like, you know, users should never see null. We can also trap all the log errors. So in the kind of field of bugs, this kind of represents, say, 20 to 30% of all the bugs. I call these the fatals. They're the big major crashes. Other things we can also catch are say, memory, excessive memory usage or excessive CPU usage, like infinite loops and stuff like that. Now I'll talk about a little bit about what we're working on. So the fatals are the kind of the obvious bugs. They're the easier ones to catch. They're also the most frustrating, like a user clicking on a button and literally nothing happens. And you're just like, oh, why is nothing happening? You know, that button is doing nothing. And then you clock it a bunch of times and then, you know, you get 10 charges on your credit card. So, you know, you shouldn't do that, but you know, we all do because it's annoying. You don't want to click on a button, but when you click on a button, something should happen always. And it should happen immediately. So the fatals are really obvious. Now, what I'm talking about on this slide is another problem, especially in web applications, is just when things get misrendered. You know, UI elements get screwed up or they're misplaced or they're rendered in the wrong color or there's some other fuck up. Those represent some number of screw ups, and the way that we can detect this is actually basically we take all of the times that web pages have been rendered correctly, and you know everything is working properly, and we can save the HTML, and we call those like the good pages, and then we take all of those web pages and we kind of screw with them in a bunch of ways. So we have your application, we render it visually, then we render it with modifications. Like we go in and we remove a class, or we change the font size, or we change the background color. We just screw with the CSS in a whole bunch of ways. And now we have a whole almost data set of screenshots showing poorly rendered websites. And like changing the font to be bigger, that can cause some kind of humorous misrenderings, like things to wrap. But also we can catch like more mangled websites by, if we change, say, the CSS display, if anyone knows the CSS display value, if you change that, it totally screws the layout of the web page. And so now we have this data set of like good looking web pages and this data set of web pages we've screwed. We can train an algorithm that can now predict, given a web page, does this look normal or does this look screwed up? And now we have a classifier that can tell the difference between like a normal web page and a mangled web page. In practice, it's a little bit more difficult. You have to very carefully choose like what classes you delete and like what CSS things you change, because you want to reflect like what are the typical UI fuck ups that real software inhabits. But once we have this classifier trained, and it's trained in a way that's sort of roughly compatible with the typical bugs that people make, now going forward, we can detect those in the future. And lastly, regression testing is something I'm working on this month. The other thing you might ask, okay, we can detect crashes and fatals and like null pointers and stuff like that. Like those are the obvious bugs. They're the more easy ones to detect. They're the ones that most tools detect. Is there a way to go further to really go from catching, say, 30% of bugs to catching 80 or 90% of bugs, like all of the legit bugs? And that's the idea that we have with regression testing. So the way that we do regression testing with AI, or at least the way that we're experimenting right now with this, let's say you have an app, you have for the last 6 months, when you press a particular button, a particular set of lines of code get executed. And if you take, button A, then button B, then button C, and you click this link over here, the same set of lines of code get executed. Some of them might have been remapped if there's been some code changes, but we can generally kind of line that up and say, oh, this function's been pretty consistent for the last 6 months. When I put this into this input box and I click this button down here, this shows up over there. Now, all of a sudden, week 9, I click this button down here and I type this in, I hit save. Now something totally different shows up over here. A null or an undefined, or even just like the value is misformatted. It might be fine. That might be actually, we might have intended to do that. We changed the code and, we fixed the formatting on the date, but could also be a bug. We didn't affect that line of code. We changed something somewhere else, and suddenly the formatting on this particular screen has changed. So the idea that we have with regression testing, it's not so much detecting a bug, but detecting a potential bug, detecting some way in which your software has changed its behavior. And if we can detect just at least some way that your software has changed in behavior, and we allow you to wait to, say, scroll through those really quickly and review which ones are real bugs, then we think that's like really useful. You can, say 1 week the software works like X, a week goes by, you made some changes, you added a new feature, you'll go onto the screen and you'll be like, oh, okay, yep, that's the new button I changed. That's the new button I added. Oh, that's a new feature I added. Oh, what's this? Oh, now that change in behavior, that's not expected. And so instead of having to go through and manually test your software, now Kwola is kind of like, it's showing you all of the things that have changed. And you don't have to go through all of the things that it doesn't think have changed. And most of those things that have changed are not bugs. They're the changes you intended because you're working on the code and you're adding new features. But one of those 1 out of 15 might actually be a bug. It only takes you 10 minutes to kind of swipe through them really quickly, and you can find a bug. And with some amount of data on which ones are bugs or which ones are not bugs, we can start to predict the probability. Okay, the software changed in this way. In this case, it's like a 70% likelihood that it's a bug. In this other case, it's only 5% likelihood that it's a bug. And there's a variety of features that go into predicting that. The last thing I want to just quickly touch on, I know we're going long here, is how do we actually reproduce the bug? So once you've found this bug, you kind of want to find like the precise sequence of actions that trigger the bug. Because if I'm a consumer, I'm watching a video and it's like, Kwola's like, clicks this, clicks that, clicks this, clicks that, goes over here, types that in over there, and then a bug gets triggered. I want to know which of all of those, 30 or something clicks actually mattered for that particular bug. And we call this the shortest path reproduction. This is something, it's literally, we've added it into Kwola last week, so it's like brand new. But the basic idea here is, it's pretty simple, actually. It's, so say we detect an error message on a particular screen. We can just run the same sequence of actions that triggered that error message over again. So it's like, I click this button, I hit this checkbox, I click this button, I get an error. All right. Okay, well, let's try that again. Let's click the button, checkbox, button again. Do we get the same error? If so, then that's definitely a bug. That's a reproducible bug. And we can now show you, okay, well, if you perform these actions in this sequence, you will definitely find the bug. But then we can go even further, because some of those actions are not actually necessary for the bug. Now you know the bug can be reproduced. Now you have, say, 30 actions, and at the end of it, you get a bug. Well, now you'd start taking actions out one at a time. So I'll take I clicked on this link. And if I take that out and I otherwise do all of the same actions, do I still get the error? And, if I take this action out, if I typed into this inbox, I take that out, I don't type into that inbox box or input box, do I still get the error? And so by kind of taking those out and it's almost like a guess and check. It's more brute force. There's no real AI here. This is a brute force strategy for reducing that whole sequence of actions where you click on 30 different things and you get a bug. And now you can reduce it and be like, it's just clicking here, and clicking here, and typing this in here. That's what triggers the bug. And we can reduce that now and show you those exact steps to reproduce. It's like, if you reliably do these 3 actions, you will reliably trigger this bug. And so now Kwola has not only found the bug for you, it's told you exactly how to reproduce it, what browser it is on, and it's showing you a video of what you need to do to reproduce that bug. And all of this can be done with literally 0 effort of your time. The regression testing thing, that'll take like 10 minutes of your time. But, for fatal errors and the majority of the bugs, it's not going to take time. You let Kwola loose on your application. It learns how your application behaves, and then it sends you bugs moving forward. And so that's what we're trying to do. So I hope that excites you. I hope that we can take reinforcement learning from being kind of a joke, and I was the one calling it a joke for many years. I'm like, reinforcement learning, that's not practical. That's not really useful. Who needs that shit? And now here I am with a real world use for reinforcement learning that we can apply to any old piece of software. As long as you can count the lines, you can train the AI, and the AI will learn how to use that program. And then we've used various techniques to find the bugs while we do it. Kwola is open source. The core you can download, you can use it for free. I love it when people use the open source software, contribute back. we actually just got it working on Windows again. So if you're a Windows user, you're not going to be left out. You don't have to be Linux anymore. That's just me. I'm a Linux guy. And we also have the cloud version. That's the less community-oriented piece. That's why I sponsored Dragos here. You can, the cloud version, if you don't have like a computer that's powerful enough, it is reinforcement learning. It requires a proper computer, nothing cheap. But if you have a computer, if you don't have that computer, use our cloud version. It's super easy. All of the models are automatically prepared. You can, you have the bugs in the user interface, and yeah, using this solution, hopefully we can totally replace the old way of doing things, going, Selenium and all of that time writing manual tests can be replaced with a more analytical approach where we analyze the software's behavior, and we learn how to use it on our own. And Kwola can self-heal. It doesn't need to, you don't need to rewrite those tests as the software moves forward. And we can hopefully take that 50% of engineering time that is spent on bugs, and we can reduce that to, say, 20 or 30%. We'll never get it to zero. Look, let's be honest here. It's always going to be bugs. But if we can get it down to 20 or 30%, worldwide, that is potentially hundreds of billions of dollars of engineering time that can now be spent on more productive uses. And so, yeah, that's it. That's how you test software using reinforcement learning and artificial intelligence.